Okay, any questions? Now, today we will continue with DC circuits, and well, probably we will have time to solve some examples. Any questions you would like to ask before we continue? Okay, so if you remember on Monday, we had discussed circuits with batteries and resistors, but what if we also input some capacitors? So that is basically what we will be discussing today in the first hour. So let's start with a very simple circuit. Let's say we have a battery which provides an EMF of V. We have a resistor, and then we have a capacitor of capacitance C. This is probably the most simplest circuit you can imagine with a capacitor and a resistor. Now, how can we find the current running through the system? So let's first imagine what will happen. Let's say we put a switch and we close the switch. So there is no charge on the capacitor. What do you expect the current to be initially? No expectations? Just make up something. At t equal to 0, there is no current running through the system yet. Then you close the switch. Oops, sorry. This is the circuit we have. At t equals 0, you close the switch. How much current do you expect would be running? No. You see, we talked about the potential. Potential was kind of this influence which causes the current, in a circuit at least, which is the influence to cause the current running through the circuit. So if this battery will try to run a current in the clockwise sense. If we had attached another battery with the other polarity, then it will try to push a current in the opposite sense. And whichever one has a larger potential, it will win. That is something we had discussed. Well, capacitor itself is also provides a potential. So it will try to drive the current in some sense, or try to drive it in the opposite sense. Initially, at t equal to 0, what is the potential of the capacitor? Okay, I heard the correct answer from some of you. At t equal to 0, what is the charge on the capacitor? 0. So the potential? 0. So the potential practically has no effect on the current. It's neither trying to run a current in one sense or the other sense. It just has no effect. So what will be the current? Initial current? V over R. It will just behave as if there is a single resistor. So Vi at t equal to 0 would be just V over R. Now let's say we wait for some time. The capacitor will be charged. So the left plate or the left terminal, let's say, will it be positively or negatively charged? It will be positively charged because it is connected to the positive terminal of the battery. So this will be a positively charged. The other plate will be negatively charged. So if there were no batteries in this system, and assuming the capacitor had those charges, what will be the direction of the current that it will try to run through the circuit? Counterclockwise sense. So at this instant, capacitor essentially behaves like a battery which is trying to drive the current in the opposite sense. So on one hand, we have the battery trying to run the current in one sense, and the capacitor trying to run it in the opposite sense. So we expect the current to decrease. So initially, there was no charge. So then the capacitor starts to get charged. So it will decrease the current. So with time, the capacitor will be charged even more, so reducing the current even more. So eventually, there will come a time when the charge in the capacitor is such that Q over C is V. So if Q over C is V, what is the current running in the system? You see, if Q over C is V, the potential difference between the points A and B is V, and the potential difference between the points C and D is also V. But D and B are at the same potential. So it basically tells me that A and C, they are also at the same potential. So there's no potential change across the resistor. All the potential change is created by the battery, and then the capacitor, they are equal. But if this is the case, there shouldn't be any potential difference between A and C. But if there's no potential difference across a resistor, then it just means that there's no current running through the resistor. So at t is infinity, we don't expect any current through the battery. So in a sense, the capacitor, in this simple circuit at least, behaves as if, when it is uncharged, it just behaves as if it is a short circuit. There's no resistance, nothing that changes the current. It's just the external resistor we have. When it is fully charged, it just behaves as if it is open circuit. It doesn't allow any current to run through. Now, any questions on how this circuit will behave? This one. So you see, are you convinced that, let's say, this, are you convinced in this? Initially, the capacitor is neutral. So the current starts running, charging the capacitor. So there will be a buildup of charge in the capacitor, so it will try to stop the current. It will try to prevent the current. But until it can exactly prevent the current will keep running, and the capacitor will keep on charging. Eventually, I claim that eventually there will come a point when the charge in the capacitor, at infinity, the charge in the capacitor Q over C, this is the potential difference across the capacitor, will be equal to V, this V over here. Eventually, there will come such a point. Now, what happens then? Now, if Q over C is V, you see Q over C is the potential difference between the two endpoints of the capacitor. So that is between A and B. At t infinity, VAB is equal to V. But you see, VAB, on one hand, this is VA minus VB minus VA. But B and D, there is no resistance between B and D. So the point B and the point D have the same potential difference. So VBA is, we can also write it as VD minus VA. So the potential difference between A and B is actually equal to the potential difference between A and D. Now let's see, on the other hand, the battery provides a potential between the points C and D, which is also V is equal to VD minus VC. That is the potential created by the battery. It's also VD minus VC. It is also V, which is equal to VAB. But now, the potential difference between the point D and A is equal to the potential difference between the point D and C. But this tells me that the point A and point C, they are at the same potential. So these two imply that potential at the point A is equal to the potential at the point C. There is no potential difference between the point A and C. But there is a resistor over there. The potential difference between across a resistor is just the current running through it times the resistance. So current running through our resistor times the resistance should be 0. That tells me that the current should be 0. So essentially, in this circuit, when we build this circuit, initially the current will be just I over R, and eventually the current will just go to 0. So this is what we expect the current to be as a function of time. That is one thing that will be different in circuits with capacitors, because with time, they are charged, so their potential changes. Oh, sorry, V over R. Now, this is what we expect. Let's see if we can actually show that this is how the potential changes. Can we calculate the functional dependence? Now, this is our circuit. Now, we will use the Kirchhoff's rules in order to calculate the current running through the circuit. But there is one thing we have to pay attention to. You see, we might end up having such a configuration, or we might end up having a configuration like this. Well, of course, with this simple circuit, it's easy to say which configuration we will have. The left plate will be charged positively, definitely. But in more complicated circuits, we will not be able to tell the difference. We will not be able to tell beforehand which plate will be positively charged, which plate will be negatively charged. Now, up to this point, when we were talking about the capacitors, we always ignored the signs. The capacitance was defined to be positive. The charge was defined to be positive. The potential was defined to be positive. Now we have to take into account the signs. That is one difference that we will have to do. Now, it's just up to you. It's a definition. It's just in your conventions, you have to be consistent. I will say the charge of the capacitor is positive if it is as on the left circuit. On the left circuit, I will define Q to be positive. On the right circuit, I will define Q to be negative. If you wish, you can just define it the other way around. It's not important as long as you are consistent. That will be important. Now let's use the Kirchhoff's rules. Let's start from the point C. Just pick up an arbitrary point you like. And we have to first decide on our loop. If you remember, the Kirchhoffs had basically two rules. One, at the junction point, the current entering the junction should be always equal to the sum of the currents leaving the junction. That's the junction rule. Well, here in this circuit, at least we don't have any junctions. The second rule was a loop rule. So if you choose an arbitrary loop, in this case, let's choose such a loop. If you choose an arbitrary loop, and if you just sum the changes in the potential across your loop, in that case, the sum should be 0. That's our second rule. So let's start from the point C. Okay, from the C to and let me also call the current I. Let me denote this current. Let's assume that the current is running in that direction. You see, also I might have been wrong in choosing the direction of the current. So basically what I'm choosing over here as the direction of the current is the positive direction of the current. If the current is positive, then it is running in the shown direction. I might end up having a current with a negative value. It just tells me that the current is running in the opposite sense. Just like I chose the sign of the charge It was a choice. So I just need to interpret my results consistent with my choice. I will be choosing the positive direction of the current. So as long as I am consistent with the directions, consistent in my conventions, if I find a negative current, it just will tell me that the current is running in the opposite direction. So I will call a current to be positive if it's running in the clockwise sense. Now, what is the potential difference between the point C and C across this loop? From the point C to the A, what is the potential drop? I times R. From the point A to the point B, what is the potential drop? It's Q over C. You see, if the charge is positive, then the point A is attached to the positive plate, point B is attached to the negative plate. So if Q is positive, then there is a potential drop of Q over C. But it will also be true if the charge was negative. You see, if this were my configuration at some time, what will tell me from the point A to point B, there is a potential increase. But an increase in potential is just a negative decrease in the potential. But if Q is negative, Q over C is already negative. So this plus Q over C is correct whether I have this configuration of charges or this configuration of charges. It doesn't make any difference. Now I'm at the point B. From the B to D, no potential change. From D to C, what is the potential drop? Minus V. So this should be equal to 0. So what are my unknowns? What are the quantities I would like to find? Or you would like to find? We want to find the current, and you see R is already given. So once you build your circuit, you already know R. You already know V. So what are the things that we don't know? I is something we don't know. And Q is something we don't know. Well, we have two unknowns. We have to find two equations. This is just one of them. Now let's try to relate I and Q. How did we define I? So we just took a point and counted the number of charges passing through that point in a given amount of time. This was the current. This is how we defined it. Now let's see, if a current dq, the small q passes through that point, what is the change in the charge of the capacitor? How are they? These, you see, this is the charge that passed through that point on the wire. This is the change in the charge of the capacitor. So how are they related? They should be the same, because whatever charge passed through that point, it was eventually came to the capacitor. So this is equal to dq by dt. And let's also just make a check. If I is positive, so the current is running in the shown direction, do you expect the rate of change of the charge in the capacitor to be positive or negative? It should be positive. So the rate of change of the charge of the capacitor, this should be positive if I is positive. So let's just put it back into our equation. So dq by dt times R plus Q over C is equal to V. Now this is what's called a differential equation. So there is a quantity whose derivative is related to the quantity itself. Now this will be easy to solve. So let's just treat that as an algebraic equation. dq is a very small change, like we had already been discussing very small integrals when we were calculating the electric field of continuous charge densities. We just divided our system into very small parts. Just like that, this dq is a very small change in the charge in the capacitor. dt is a very small change in time. Well, I can just treat this as an algebraic equation. Let me just simplify it a bit. This is equal to v over r, or dq by dt. This is v over r divided by q over rc. Now I'm treating it as the ratio of very small changes. A very small change in time is related to a very small change in the charge through this relationship at an arbitrary time. Now I can just sum all these small changes in time. So let's say that I'm summing all these dt's from a t equal to 0 to some final t, and then I'm just summing all these quantities during the same time. So that is nothing but an integral from some t equal to 0 up to, let's say, a capital T. If I sum the small dt's between these two integrals and sum these things between those same interval, q at t is equal to 0 and q at t is equal to t, they should still be equal. And I will assume that initially there is no charge in the capacitor. The initial charge is 0. And q at the time t is equal to t is just q of t. So what is the integral on the left? Logarithm of what? Well, let's say v over r minus q over rc. If you take the derivative of this thing with respect to q, you get 1 over this quantity multiplied by derivative of inside, which is minus 1 over rc. So I have to multiply it with minus rc. So that when I take the derivative of this quantity with respect to q, I recover my integrand. Q changes from 0 up to q of t. And this should be equal to the right-hand side is t. Now I just need to do some algebra to simplify this a bit. So logarithm of v over r minus q over rc minus the logarithm of v over r, this is equal to minus t over rc. I just divided by minus rc both sides and just took the integral. Now I know the properties of the logarithm. The left-hand side is just the ratio of v over r minus q over rc divided by v over r minus t over rc. So this quantity over here, let me also simplify it a bit. This divided by this is 1 minus q over vc. Well, when I divide 1 over rc with v over r, r's cancel, I end up having v. This should be equal to e to the power minus t over rc. Or q is equal to v times c, 1 minus e to the power minus t over rc. This is the charge in the capacitor as a function of time. Now let's see how that changes with time. When t is equal to 0, this is just 1. 1 minus 1 is 0. Well, that was our initial condition anyway. So as a function of time, this is, let me use the small t now. We start from 0. As time increases, this becomes smaller and smaller. So this difference becomes larger and larger. So the Q increases with time. And when t is infinity, when t becomes very, very enormously large, Q just becomes C times V. So Q increases, but the increase slows down, and only asymptotically it reaches V times C. But that was also something that we expected. We expected that eventually Q over C should be equal to V. So that is the final value of the charge on the capacitor. Now we can find the current. You see, we had already related the current to the charge in the capacitor. This is equal to d by dt, v times c times 1 minus e to the power minus t over rc. So if you just take that derivative, minus vc times minus 1 over rc, e to the power minus t over rc. So these c's cancel, minus minus cancels. So the current is v over r, e to the power minus t over rc. So when t is equal to 0, the current is v over r, as if there's no capacitor. And as t increases, the current just goes to 0. So we started at v over r, and it goes to 0 even asymptotically. Any questions? This one. Well, let's do another example, a discharging capacitor, and we will discuss it again there. Any questions on this one? Well, you can use this if you want to build a blinking light. Let's just imagine this circuit. You have a battery. And here you have a gas discharge tube. Well, this is essentially a tube with a low pressure gas, any gas that you like. The idea of low pressure is that if it is at low pressure, the electrical breakdown potential will be lower. So basically, if there is the potential difference between the points A and B, if VAB is larger than some critical value, then you get an electric discharge through this tube, and it will glow. You will get light. Now, the battery that you have there, you should also put some resistor. The resistor is always there. You cannot avoid the resistance. So if V is large enough, larger than that critical value, so there will always be a current running through it, and the current will be V over the resistance of this one divided by the resistance of this one. So you have continuous light in this case. Now let's imagine we put a capacitor over here with a capacitance C. Initially, the capacitor is not charged. So what is the potential difference between these 2 points? 0. So the potential difference between A and B is 0. So if you would plot VAB as a function of time t, initially the potential is 0. Let's say the critical potential is over here. This is V critical. V over C, now V is somewhere over here. This is V. Initially, the battery is not charged, so the potential across is 0. As the battery is charged, the potential will increase. When it reaches the critical value, there will be a discharge. But when there is a discharge, the resistance of that tube is negligible. So it essentially just drains all the charge in the capacitor. So at that instant, the charge will almost immediately go to 0. Now the potential between A and B is now below V critical, so there won't be any discharge. So the charge will start building on the capacitor. As the charge is building up on the capacitor, the potential difference will increase, and when it reaches the critical value, it will just short. And by choosing your capacitance, you can adjust this time. So this circuit will just, the light will blink, blink, blink. Here, you see, in this discharge tubes, when there is an electric current running through it, essentially you have a plasma inside. You have free charges, free electrons and free ions. But free charges, they don't have any resistance. So the resistance is essentially 0. Since the resistance is 0, all the charge in the capacitor will just short. So all the charge of the capacitor will dissipate, will just go away. It will neutralize. So by adjusting the capacitance, you can even adjust the time interval between these blinks. Well, if you don't want your blinks to be very short in time, I mean, there is a light and it just goes off, then you should better put some resistance over here also, a small one. You see, what will happen if there is a small one over there is that, well, initially there is no current running through that second resistor, that, let's say, R2. Initially there is no current running through that R2, so all the current goes to the capacitor. But now there is a short over there, so there we have a different circuit. We have this circuit. We have such a circuit. There is initial charge in the capacitor, and we have this resistor. This resistor will slow down the current, so the capacitor will not discharge immediately. It will take a finite amount of time. So what you will have in this system is you will have no light. The light will go on, turn on. It will stay some time, and then it goes down, etc. And by just adjusting those two resistances, you can just adjust what is the interval between the two on times of the light and how long it stays. Now let's also study this circuit. Now if you have such a circuit, initially if the capacitor is not charged, is neutral, you won't get any current. Nothing that drives the current. So let's assume that initially the capacitor has some charge Q0. Then this charge, the capacitor will try to discharge through the resistor, and there will be a time-dependent current running through the system. And this is the resistance. And the charge in the capacitor will also change as a function of time. So let's just choose an arbitrary time. At an arbitrary time, the capacitor has a charge Q, and the current running through the system is I. Okay, first we have to fix our conventions of the positive charge, positive current, negative charge, negative current. So let's just say that I will choose the charge in the capacitor to be positive if this plate is positively charged, the above plate is negatively charged. That is what I will call to be a positive charge. And I will call the current to be positive if it is running in this direction. Well, more or less like in the previous case. If the current is charging the capacitor, I also chose the current to be positive. I repeat, it's just a matter of convention. You can choose whichever you like. It will not change the result. Again, we will just use the Kirchhoff's rules. The potential difference between the points A is 0. Let us choose some loop. Let me choose my loop. This time in this sense. And let's see what will happen. I'm going around the loop in the counterclockwise sense. What is the potential difference between the point A and B? 0. What is the potential drop as we go from B to C? Well, it should be Q over C. But you see, if the charge Q is positive, charge like this, then there is a potential increase, which I can write as a negative potential drop, minus Q over C. Now, what is the potential difference between potential drop as I go from C to D? 0. What is the potential drop as I go from the point D to A? I times R, but let's pay attention to the signs. You see, I'm choosing the positive current to run in this sense. So if there is a positive current, as I go from D to A, there is actually a potential increase because the current always runs from the higher potential to the lower potential. As I go from D to A, there is a potential increase, so I should write a negative potential decrease. So this is the equation I obtained from the loop rule. Now I need to use the definition of the charge. I is at the same time dq by dt. This is how we define the current. And this dq is essentially just on the wire. Pick any point. This point. There is a charge dq passing in that sense in a time dt. So that is how we define the current. Now, if a charge passes through this point, if a charge dq passes through this point, it increases the charge of the capacitor. So this dq, which is the charges passing through this point over here, is at the same time the change in the charge in the capacitor. So this should be, since dq is equal to the capital Q, this is equal to dq by dt. And let's go back. Let's put it in our equation. Minus q over c minus r dq by dt. This is equal to 0. Or dq by dt, this should be equal to minus 1 over rc times q. Or this tells me that dq over q is equal to minus 1 over rc dt. Now I can integrate both sides from 0 to t. And this goes from at t equal to 0, the total charge is q0. And eventually, the total charge is q of t. Well, the left-hand side, the integral is logarithm of q from q0 to q of t. The right-hand side is minus 1 over rc times t, which, okay, I will just jump some algebra. Q of t is equal to q0 e to power minus 1 over rc times t. At least everybody woke up. Now, any questions? Is the most crucial thing over here, that is the physics part, let's say, is to write down the Kirchhoff's rules. The rest is calculus, some algebra. Now, let's solve this same problem with slightly different conventions. Let's say this is positive, this is negative, this is my positive Q. But this time I will choose the current to be positive if it is running in the opposite sense. What will change in this case? Again, I will use exactly the same loop. This is the point A, B, C, D. And again, VAA should be 0. So as I go from the point A to point B, what is the change in the potential? 0. As I go from point B to point C, what is the potential drop? The potential difference across the capacitor is Q over C, but since it's an increase, not a drop, I write it as a negative drop. From the point C to point D, 0. From the point D to point A, what is the potential drop? Plus or negative? Minus. This time it is plus. The current is running from D to A. So there is a potential drop if the current is positive, of course. Now, how can I relate I to the charge in the capacitor? This is the next step. What is the relation between a very small amount of charge that runs through my wire and the change in the charge of my capacitor? Well, if dq is positive, that is, through this point, a small amount of charge passed in this direction, then the charge in my capacitor is decreasing now. So if the change in the charge in the capacitor is this one, this is minus if this is positive, plus. This is negative if this is positive. So I have to put a minus sign there. So this is the current is minus the rate of change of the charge in the capacitor. Now if we put back minus Q over C minus dq over dt r is equal to 0. Well, this is in fact exactly the same equation that we wrote before. So I change my convention. Instead of choosing the current to be positive in that direction, now I choose it to be positive in this direction. But a change in the convention doesn't make any difference. It shouldn't make any difference. As long as you are consistent. You see, I change the positive direction of the current in this equation, but to be consistent, that changed reflected to another change over here. So because I have been consistent, I have the same equation, same result, essentially. You see, what did I say? D small q is from the definition of the current. You have this wire, you pick up a point on the wire, and you count how many charges passes in one direction. That is what our D small q is. But at the same time, I have my capacitor. The capital Q is the amount of charge in this plate. It can be positive, negative, but at the end of the day, it's the charge in that plate. Okay. Now, I chose my positive direction of the current like this. So if you take your this is my battery, let's say. This is my positive plate. This is my positive plate. This is the second plate. Small dq amount of charge moves in this direction, the positive direction of the current. But that charge came from my capacitor. The charge in the capacitor has decreased. So if this D small q is positive, then I know that the change in the charge in my capacitor should be negative and equal in magnitude. So they are equal in magnitude, but this one is negative if this one is positive. So if I want to write an equality, I have to introduce another minus sign. That is why I have this minus sign over here. Because I already know that if one is positive, the other one is negative. Other questions? Any examples that you would like me to solve? Okay, so let's discuss this example of jump starting a car. Do you know what is a jump starting a car? No? How many of you are driving cars? So what do you do if the battery in your car is dead? This is it. Oh, no, this is not it, sorry. Vurdurmak is somebody pushes it, right? No, this is not it. You just bring another car with a working battery, and you just connect the positive terminal of the working car to the positive terminal of your batteries, your car's battery, and the negative terminal to the negative terminal. So essentially, this is your bad battery. This is the good battery. This is bad. You just connect the positive terminals together and the negative terminals together. And then here is your car. And you just hope that the good battery provides enough current to your car so that it will start. Now, what does it mean to have a bad battery? Any ideas? It doesn't have to be a car battery. I mean, it can be a bad battery in your cellular phones. It ran out. What does it mean? The potential is lower than what is necessary. So let's say that let's call this V0, this is V1. Ideally, you would expect your car battery to be something like 1.2 volts, but this goes, 12, you expect 12 volts, it goes down to 10 volts or something like that. So V0 is larger than the nominal, which is something around V1. Now, of course, each one of these batteries themselves have their resistances. Let's just call them to be the same. This is the small r. So the question is, what will be the currents running through my system? Will I be charging my battery, the weak battery? Well, we will see next hour. Any last questions? Okay, see you in 10 minutes.